Hi, fifth graders. We're going to kick off our unit on decimal multiplication by bringing back those powers of 10 and using some mental math strategies. So the big idea here is that we can use mental math to help us solve decimal multiplication and eventually even decimal division problems by finding some patterns. So a quick refresher, powers of 10 could be written in a couple different ways. We can see them in standard form, which is just the number version. We can see powers of 10 written as an exponent, like 10 to the third. We could see them in expanded form, where it stretches out how you would get that answer. Or we could see it in word form, like the fifth power of 10. And all of these so far are whole number powers of 10, because that's all we've worked with so far. But now that we're in the decimals units, we're going to find that we can also have decimal powers of 10. And just like whole number powers of 10 follow the pattern of 1, 10, 100, 1000, that same idea is going to be true with the decimal powers of 10. We're going to have 1/10, 1/100th, 1/1000th, and so on. So let's take a look today at multiplying by both whole number powers of 10 and decimal powers of 10. So first, when we multiply whole number powers of 10, this pattern probably looks really familiar to you because we talked a lot about this at the very beginning of our year when we talked about place value and multiplying by whole numbers. I can see very quickly that in my pattern, my powers of 10 are all represented by exponents. So I know that every whole number has a decimal point on the end. And this is when that idea is going to become really important. Now, for the first example in that pattern, 24 times 10 to the 0 power, hopefully you remember that 10 to the 0 power is just like saying we're multiplying by 1. So this particular example is just saying 24 times 1, which we know is 24. Now, here's a chance where we get to stretch your thinking a little bit. So all along in your math career, you have talked about multiplying by whole number powers of 10 as adding zeros onto the end of your number. For example, you might be looking at this question and saying, 24 times 10 to the first, well, that's 240 because I add 1 0. And up until now, that answer would have been 100% correct. But now that we're talking about decimals, I get to teach you that there's actually been something else going on behind the scenes. Really, what we're doing, instead of just adding on zeros, we're actually putting those zeros in as placeholders because we're really shifting the decimal point. In other words, in 24 times 10 to the first, I know I have the whole number 24 followed by a decimal point. Since I'm multiplying by a whole number power of 10, that means my answer is going to get greater. So really what's been happening all along is I've been shifting this decimal point the same amount of spaces as we know from our exponent. So if I shift that decimal point one space, it's going to leave an opening where I need to fill in a placeholder 0. That's why up until now, you've just added zeros on. But when we start dealing with decimal numbers, you won't always add on zeros. You'll only add them in when you need them as a placeholder. Let's finish off this pattern here. So when I have 24 times 10 to the second, 10 to the second is like saying 100. I see an exponent of 2. That tells me I need to shift that decimal point 2 place value positions so that my answer becomes greater by 2 place value positions. So if I'm shifting once and twice, I can fill in those empty loops with placeholder zeros to give me a final answer of 2,400. Same thing at 24 times 10 to the third. I have 24 with my decimal point on the end. I need to shift that decimal point 3 spaces, 1, 2, 3. And then finally, I need to fill in those 3 empty spaces with placeholder zeros for a final product of 24,000. So the big idea here is that since the product gets greater, we're shifting the decimal point to the right the same number of spaces as there are zeros. And in exponent form, we can find that out just by looking at the exponent. Now let's take a look at what happens when we multiply by a decimal power of 10. 24 times 1 still stays 24, so we can start off our pattern the same way. But now when we're multiplying by a decimal power of 10, what I'm doing is I'm multiplying by something that's less than 1 whole. When I multiply by something that's less than 1 whole, my product is going to become less. So now I need to take that idea of shifting the decimal point, but I need to move the decimal point in the opposite direction. Since my product is going to become less, I need to shift my decimal point to the left. And the way I know how many spaces to do that is by counting the number of digits after the decimal point. So in 24 times 0 and 1/10, there's only one digit after the decimal point. So I'll start with my whole number 24, and I'll shift that decimal point one space to the left. That means my answer now becomes 2 4/10. And in 24 times 1/100th, now I have two digits after the decimal point. So I'll start with my whole number 24, and I'll shift that decimal point two spaces to the left. 1, 2, puts it in front of there. You can add a placeholder 0 in the ones place if you'd like to, or you don't have to, you could leave it off, but either way, your product would be 24 hundredths. Finally, in 24 times 1,000th, since I have three digits after the decimal point, I need to shift my decimal point three spaces to the left. That means I go 1, 2, 3, and I place it here. Just like with whole numbers, sometimes I need a placeholder 0. So my product here is 0 and 24 thousandths. So again, the big idea is that since my product becomes less, I need to move my decimal point to the left, the same number of spaces as there are digits after the decimal point. Okay, now you might be wondering, well, wait a second, when have you ever seen patterns like this in real life? And truthfully, you don't. But they do come up in two different ways. So we can look at different word problems in different scenarios with powers of 10 patterns when we're making equal groups and also when we're doing some resizing. So let's take a look at a quick example of each of these types of word problems. So the first example I have is Cindy is combining equal-sized rectangles to make a postage stamp quilt. Each rectangle has an area of 0 and 75 hundredths of a square inch. If she uses 1,000 rectangles to make the quilt, what will be the area of the quilt? Okay, so first of all, I didn't know this for a long time, but a postage stamp quilt is just a quilt that's made up of tiny little squares of fabric. It's not actually made up of the stamps that you put on the corner of an envelope. So if I'm going line by line, that first sentence now tells me that Cindy's making all these little rectangles and putting them together into this quilt. So you can kind of see what that looks like with the picture. Now the second sentence tells me each rectangle has an area of 75 hundredths of a square inch. So that means that each tiny little rectangle is 0 and 75 hundredths inches squared. Finally, the third sentence I'm going to break into two sections. The first says, if she uses 1,000 rectangles to make the quilt. Okay, well that part tells me that we need 1,000 sets of those little squares. And the question part asks, what will be the area of the quilt? So this means I'm taking 0 and 75 hundredths and I'm multiplying it by 1,000. So I can apply that patterns rule by counting the number of zeros in my power of 10. Since there's three zeros, what that means is I can shift my decimal point three spaces to the right because I'm getting greater. So I'll highlight that decimal point there in between the digits 0 and 7, and I'll shift it 1, 2, 3 spaces to the right, which means now I need to fill in that empty loop next to the 5 with a placeholder 0. So my final answer would be 750 inches squared as the final area of the quilt. So that's an example where we're making equal groups because we made 1,000 sets of those small rectangles. Let's take a look at a resizing example. This example says, Jorge is making a scale model of the Willis Tower in Chicago for a theater set. The height of the tower is 1,353 feet. If the model is 1/100th of the actual size of the building, how tall is the model? Okay, so if I'm going line by line now, I know it says Jorge is making a scale model of the Willis Tower in Chicago for a theater set. So this is a picture of the Willis Tower in Chicago. So he's trying to recreate this for a play. The next sentence says the height of the tower is 1,353 feet. That means if I were to go to Chicago and measure it, it would be 1,353 feet tall. I'm going to break up the next sentence into two parts. The first part says, if the model is 1/100th of the actual size of the building, and here's the key part that tells you you are resizing. Whenever you have a number next to the word of, you are going to multiply. The number of combination tells you to multiply because it's a resizing question. This 1/100th is just a decimal in fraction form. So the question is asking us, how tall is the model? Now that I see that number of combination and I know that I need to multiply, I can take 1,353 and multiply it times 1/100th. Since I'm multiplying by a number less than 1, I need to shift my decimal point to the left because my answer will get less. And that makes sense because if you're making a model of something, the model is going to be smaller than the actual tower. Since there are 2 zeros in my power of 10, I'll shift that decimal point 2 spaces to the left, which means the model will be 13 and 53/100ths feet tall. We'll do lots more examples with these, but I just wanted to show you a mental math power of 10 strategy with decimals.